Okay, the topic of this review module is units, and you can find more supplemental information in the Harvey e-text and examples in section 2B, and of course obtain the PowerPoint from Angel. Okay, so obviously, of course, we're all familiar with metric and SI-based units and simple unit conversions, so I'm not even going to touch on those things. And of course, we're also familiar with the beauty of the metric system in that it's based on factors of 10. Alright, so just a very quick reminder, if you struggle and get mixed up with the zeros when converting between units, say for example, we had a measurement of 132 micrometers. Alright, and so we can look and see a micrometer is 1/1,000,000th or 1 × 10⁻⁶ meters. So if we want to convert, of course, to cancel out our micrometers, we put that in the denominator, our meters into the numerator, if we're going to meters. Okay, and so one way you could write this, in the numerator, 1 meter is equivalent to 1 × 10⁻⁶ micrometers. Or another way we could look at it, we could flip it and say 1 micrometer is 1 × 10⁻⁶ meters. Or we could say 1 meter is 10 to the 6th micrometer. There's 1,000,000 in 1 meter. Okay. Either way, we can do the math, and we'd come up with 1.32 × 10 to the -4th molar. So if you struggle getting those zeros switched around converting units, just think of it as a simple unit conversion. Okay. Next, one other special type of unit conversion is when we're dealing with multiple dimensions. And so I'll let you take a minute to look at this problem, so go ahead and pause the video for a minute to give it a try. Alright, come on now. Did you really pause it? Okay, so if we looked at this very quickly, we might just try to take our 591 cubic centimeters and then use our conversion factor 1 inch per 2.54 cubic centimeters. Alright, so we get 233. But then if we look at our unit analysis, I'm sorry, this is just 2.54 centimeters. So if we did this, our units would be inches, then we have centimeters cubed divided by centimeters is centimeters squared, which doesn't make any sense. Okay, and so if we're dealing in multiple dimensions, we first have to take our conversion factor, 1 inch equals 2.54 centimeters, and we have to put the conversion factor into multiple dimensions. So we're dealing with cubic units, so we'll square both sides. I'm sorry, cube. And so we'll cube the number and the unit. So 1 cubed is still 1 inches cubed. Okay. Again, cube the number, cube the associated unit. And so 2.54 cubed is 16.39 centimeters cubed. Okay. Once we have this appropriate conversion factor, then we can use it, take our 591, divide by 16.39, and that will give us our actual correct cubic inches. Okay. Alright, and just a simple visual to illustrate that, obviously, if we're dealing in 1 dimension, 1 yard is 3 feet. If we're dealing in 2 dimensions, 1 square yard is 9 square feet, and then 1 cubic yard would be 27. Okay. Alright. Next we're going to take a look at concentration units. Alright, and so obviously we're familiar with molarity, moles solute per liters of solution, the total solution. Alright, molality on the other hand is moles solute per kilogram of only solvent, not including the mass of the solute. Okay, so here's an example. I'll let you pause and take a look through that if you'd like just a quick refresher on calculating molarity and molality. Okay, so this is a concentrated sample, and so the molarity and the molality come out to be significantly different. Alright, but in general, for dilute solutions, since water has a density of 1 kilogram per liter, if we have a dilute aqueous solution, typically the density is not going to change much from this. Okay, and so 1 liter is equivalent to 1 kilogram. And so because of that, for these dilute aqueous solutions, the molarity will generally approximately equal to molality. That was not the case on this previous example because it was so concentrated. But when it's fairly dilute, this will generally be the case. Okay. So what's the point at having two different mole-based concentration units? Well, if we look at the temperature, we know that as the temperature increases, say from 25 to 55 Celsius, that causes the volume of water to expand. So if we originally prepare our solution right to the line, if we heat it up, the volume will expand and go above that line. Okay? And so if we were calculating our molarity, moles per liter, well, if we heat it up, the liters have gotten bigger. So we're dividing by a bigger number. So as temperature increases, molarity actually gets smaller. All right? Whereas even when the temperature increases, since molality is mass-based, the mass isn't going to change like the volume does. And so as the temperature increases, the molarity will not change. Okay? And so when we're dealing with situations where you have temperature fluctuations, it would generally be better to use molality, which is temperature independent. Okay. Let's look at a number of other concentration type units. Okay, so of course you're familiar with mass percent. Just take the mass of our component over the mass of the whole solution, write it as a percentage. Alright, so this is often used for solid solutions. For example, steel, which is a solution composed of several metals that have been homogeneously mixed when it was melted. Okay, and you often just see that written as the weight percent. Okay, likewise, volume percent of the one component over the whole solution. Alright, so if you're working for Great Lakes Brewery and you need to determine the alcohol content in a new beer, you'd measure the volume of alcohol relative to the volume of the whole solution. Okay. One important thing to note here is that surprisingly, if you mix two substances, say ethanol and water together, 50 mils of each, you do not actually get exactly 100 mils of solution. And the reason for that is because when the ethanol and water molecules interact with each other on a molecular level, they pack together tighter, and so 50 mils of ethanol plus 50 mils of water actually equals a little bit less than 100 mils. Alright, this is why we don't just take in our graduated cylinder and mix two solutions together. We always use the volumetric flask so we know the total volume is exactly what we think it is. Okay, and you often see this expressed as just a volume percent or volume per volume. Okay, all right, and then a mixture of the last two units is a mass per volume. All right, so this is often used for aqueous solutions. For example, you might say a person had a concentration of 55 micrograms per liter of potassium in their blood. Okay, and this is expressed as weight per volume. Okay. One thing to note that if you just see a number reported with a percent and it doesn't say weight per volume or volume percent, assume generally that it means weight percent. Alright, if it's not specified beyond that, if you're just given a percent, assume that. Okay. And then lastly, our last units we'll look at are parts per million. Okay, and of course what this means, say you had a solution that was 5 parts per million chloride. What that would mean is if you had 1,000,000 grams of the solution, 6 grams of that would be from the chloride. Okay, and to help simplify it for you, notice that this is basically the same formula we used for mass percent. Right, massive component per massive solution. Same thing. Instead of multiplying by 100, we multiply by 1,000,000. Okay, and so you can think of a mass percent as parts per 100, this as parts per million. Okay, so basically the same type of idea, instead of the basis is not 100 but 1,000,000. Alright, and then of course the analogy would further carry on for parts per billion, which is the same thing, except on a larger basis. Okay, and so why do we have all these other different types of units? Well, one of the main reasons is that scientists in different fields like different types of units. For example, a doctor might like to see an analysis for their patient recorded in a certain type of units because that's just the standard units that they use in the medical field. Where an environmental scientist might use a completely different type of unit. And so we need to be familiar with these, and we also need to know how to convert between them, because often we'll perform an analysis, get the molarity, but then we'll have to communicate that concentration to someone in a different field in the units that they're typically familiar with. Okay, so next we're going to wrap up with a couple examples of conversions between concentrations. Okay, so here we have a soda sample with 121 ppm caffeine. Okay, and so we could write this as if we had 1,000,000 grams of soda, 121 grams would be from the caffeine. Okay, 121 parts per million. All right, and we want to get the molarity of this. Okay, so what we want to get to ultimately is the moles of caffeine relative to the liters of the soda. Okay, and so the way that I would suggest thinking about this is kind of a double unit conversion. So first we have to convert the caffeine from grams to moles. Then we have to convert the soda from grams to liters. So let's focus on the first part, the caffeine. Alright, so here we're given the molar mass. So we can take this, multiply 1 mole of caffeine has a mass of 194.19 grams. Okay, so now we have moles of caffeine per gram of soda. So we've done that first conversion. Now we have to convert the grams of soda into liters. All right, so we have to think, how do we get between liters and mass? Well, that will typically be done using our density. Okay. All right, and so we want to get between grams and liters. So we might rewrite this and say if there's 1 gram per 1 milliliter, there would be 1,000 grams per liter. Okay, so just kind of rewriting our density. Okay, and so taking this then, we would say 1,000 grams of solution takes up a volume of 1 liter, just applying the density there. Okay, and so our grams of soda canceled out, and we're left with moles of caffeine per liter of the total solution. Okay, and so this comes out to 6.23 times 10 to the minus 4th molar. Okay, so just convert the numerator, then convert the denominator. All right, one last example. What's the weight percent of a 0.2 molar solution of concentrated HCl? All right, so again, if we start out writing our original quantity as a ratio, that would give us 0.2 moles of HCl per 1 liter, because molarity is moles per liter. Okay, so first of all, start out by writing it as a fraction. All right, and then again, ultimately, we want to get the weight percent, which would be the mass of HCl per the mass of the whole solution, and then times 100 to write that as a percent. Okay, so again, just think of it as a double unit conversion. First we'll convert from moles into mass for HCl. Okay, and so we could quickly calculate the molar mass of HCl, which is 36.45 grams. 36.457 to be exact. Grams of HCl per every 1 mole of it. Okay. So now our numerator is in the correct units that we want, mass HCl. And so lastly, we have to convert our volume of the solution into mass. And again, that conversion will always be done using our density. Okay. And so again, here we're dealing with liters, So if there's 1.05 grams per milliliter, if we multiply both by 1,000, that would be 1,050 grams per liter. Okay, and we want to get the liters to cancel out, so we'll put the 1 liter in the numerator to cancel, and the 1,050 grams in the denominator. Okay, so our liters cancel, and we're left with moles HCl, mass HCl per mass of solution, also in grams. Okay, so we have this component, and then to get it as a mass percent, we'll just multiply that by 100. And so this would come to 0.694% HCl. Okay, and then just double checking our significant figures. Both of our numbers given had 3. We're doing all multiplication and division, so our final answer will be limited to 3 significant figures as well. Alright, so I'll now leave you to look at the associated problems on Sapling Learning.